Okay, welcome. Let's look at Chapter 2, Section 1. We're going to divide this into a couple days. The first day we're going to focus on what is a derivative and a tangent line. So we're going to look to find the slope of the tangent line at a point, which that'll be interesting. And we'll use the limit definition to find the derivative. So some new vocabulary coming your way. Derivatives. What is a derivative? Well, derivatives inform us about how fast something's changing. So derivatives are all about change. Often you'll hear us talk about the rate of change at some point. A derivative gives us the slope of the curve at a point. And in the past, we've defined slope, you're familiar with this, as the amount of change in the y direction compared to the change in the x direction, the rise over the run, which was a rate of change. So that still is gonna be our thought pattern here. It's the amount of change of y over the change of x. A derivative is also called a difference quotient. But what's a little bit different than the slope that you learned in algebra and subsequent classes, we always had this formula, right? y2 minus y1 over x2 minus x1, where we were looking for the difference of the y's over the difference of the x's. We use 2 points to calculate that. So for a secant line, the slope of the secant line can be calculated using 2 points. And we can refer to that slope as the average rate of change. In our picture here, why don't you go ahead and place Q, well, you can put it a little ways away from P, and then let's draw a line through that. So I'm going to try and sketch a pretty straight line through there. This is what's known as a secant line. It passes through 2 points, continues on. We could calculate the slope for that secant line, and all we needed to do was get 2 points, right? Look for our ordered pairs. And then we do the y2 minus y1 over x2 minus x1. What I'm going to do is say I have x as my point, and then let's follow Q down here. I'm going to call this x plus a little bit. I'm going to call it x plus h. I'm going to switch to an h here instead of delta x. So this Q point has a coordinate for x at x plus h. That means that we have a change here of h. H represents the amount of change in x for us. We also have P. P is sitting at a height of f of x. And Q, well, Q would sit at a height of f evaluated at x plus h. Put in our x value, get out the y value, right? And that'd be great. I could calculate out my slope on this. I could have f of x plus h as my y2 minus f of x divided by x plus h, the difference of my x values. This would look like x plus h minus f of x. And on the bottom, x minus x goes away and it'll just be an h there. Well, for the notion of a derivative, what we want to do is bring this q in ever so close to p. I want to minimize this change of x and bring it super tiny so that I'm bringing in, whoops, those didn't stay together, so that I'm bringing in those points and bringing them close together. Then that changes the look of my secant line, doesn't it? Secant line now takes on a little bit different slope, and it would change as that q value started coming down closer and closer, right? Well, a derivative is defined as bringing this change of x, represented by h here, to a very, very small amount. I want h to go to 0. And if I do that, then q becomes on top of p, and I'm really talking now about a line that is tangent to my curve. Okay? It now is a tangent line. And how would I calculate the slope on this tangent line? Well, that's really the job of a derivative. I don't have anything there. The job of a derivative is to calculate the slope of a tangent line at a particular point. So, the derivative gives us the slope of a curve at a point, which is a little different than a secant line, because a secant line uses 2 points. The definition of a derivative, the derivative of the function f at x, is defined by, here's some new notation. This is f prime of x. It indicates it's a derivative, which is really a slope. And here's the formula. Like we talked about, we want that point Q and P to come together. Remember how we brought Q down to P? I need these separated on that previous page, so that the difference between our x values was only this small amount of h. Now we're going to let h go to nothing. We want it to be very little difference. And we'll evaluate, this is like our y2 minus our y1 point, and x2 minus x1 will result in h. X plus h minus x leaves us just h in the bottom. So really, all we need to do is calculate the limit as h goes to 0 of this function. F prime of c is the slope of the tangent line at x equals c. There's an alternate definition for derivative at a point. This is kind of the key difference. This one is at a point, where this one is really just generalized at any x. So this one is f prime of c at a particular point, and you can see the formula is just a little bit different. F of x minus f of c over x minus c. And sometimes that's easier to use, a little less complicated, and it will give us the slope of the tangent line. So let's go through a problem. You might want to write not super large, because there's going to be probably about 6-7 steps we'll use to get our answer here. Use the definition of a derivative to find the slope of the graph. And our function is an easy function. We can see it's linear. And I bet you know what the slope of this line is going to be already, because since it's a linear function, we can read right now that the slope is always staying constant at 3. Well, then every point along this line should also take on, whoops, that's pretty close, a slope of 3, because it's never changing, it's constant. So I'm going to go up 3 over 1. Here's my mark, and I'm going to go through -2, since that's my b value, mx plus b format. And I know all along here, this slope is always 3. So what I'm doing is taking a problem that we know the answer to, that we should be able to find f prime of x, and it's equal to 3. We're going to do it through the limit process. So here we start. F prime of x is equal to the limit as h approaches 0. We want to evaluate our function at f of x plus h. So I'm just going to write down my formula to start us off so that you know what we're plugging in and where it came from. So there's the format for a derivative. So f prime of x as the limit taken at h going to 0. Get it, spit it out here though. Now, let's evaluate our function at x plus h. So I replace, right? At x, I replace it with x plus h. So I have 3. If you have a different color pen, maybe it would be a good idea to show how you're substituting. I'm putting in x plus h in that x position, and then -2. That is the first part. I've got that function done. Now it says minus, okay, minus. Now I've got to evaluate f at x. Well, that's what this says. So here's the second part. It's 3x minus 2. I'm purposely using those brackets just to accentuate the fact that this was f of x, and this is f of x plus h. Okay? Now, from here on out, it is totally algebra. The calculus part of this was setting up the limit. So let's distribute. We'll get 3x plus 3h minus 2. Distribute your negative, 3x plus 2 divided by h. Keep simplifying. F prime of x is equal to, continue to write the word limit because that's the function we want to do. Minus 3x, positive 3x, minus 2, positive 2. Well, look there. I've got a 3h on top over an h. Excellent. Because now my h's are going to cancel. H divided by h gives me 1. The limit as h goes to 0 of 3, well, the limit of a constant is the constant, isn't it? And voila, no big surprise, we came out with the derivative equaling 3. Remember, a derivative, rate of change, actually instantaneous rate of change. So the next question here, number 3, find the slope of the line tangent at x equals negative 3. Well, at x equals negative 3, where would I be? Somewhere over in here. I'd be down in here. What's the slope at that spot? Well, it also continues to stay 3. F prime of negative 3 is still 3. No matter what x I put into my function, I am always coming out with 3. So not too hard to evaluate. Is the derivative a function? Okay, what is that asking? We knew that f prime of x was equal to 3. Well, this is like saying, I mean, this is function notation, it's a derivative notation, but really ask yourself, is y equal 3 a function? Yes, it is a function. It passes the vertical line test. So derivatives, one of our conclusions is derivatives can be functions as well as the original function that we started with. So derivatives can be functions. Cool. Another problem. Now this one gets a little bit more difficult. And what time? We're at 12 minutes. Let's keep going on this video. Find the slope of the line tangent to the graph of the function at a given point. And they want us to evaluate at the point x equals 2. I gave you a picture over here at x equals 2. Put in 2. I don't know what we get out, but somewhere about up in there, right? Hey, draw me a picture of a tangent line. We want it to just, skim by there, just touching, and get a feel for the slope, the angle of that line. All right, so part 1, f prime of x. Well, here we go again. The limit as h goes to 0. This is a formula you're going to want to memorize. F of x plus h minus f of x over h. F prime of x equals the limit. Now let's actually use our function. Our function was x squared plus 4x. So I need to substitute for x there and there, right? What do I substitute with? X plus h. So I need x plus h quantity squared plus 4x plus h minus 1. This was all coming from the evaluation of f evaluated at x plus h. Subtract. Now let's get the second part of our function. Now we're doing this one, f of x. Well, f of x is as shown, x squared plus 4x minus 1. That is all divided by h. So there we go. We have the layout. Now let's expand that squaring. and simplify what we can. So I'm going to get the limit, because you're always writing this down. The limit as h goes to 0. Square this, and we're going to have x squared plus 2xh plus h squared. Distribute gives me plus 4x plus 4h minus 1. Distribute the negative, minus x squared minus 4x plus 1. Probably one of the longest fractions you've ever written. There are many things that are going to 0. Positive 4x, negative 4x. Negative 1, positive 1. Negative x squared, positive x squared. What does it leave us with? The limit as h goes to 0. Okay, so I'm going to use my highlighter and just looking for things that were left. That term, that term, that term. And the thing I noticed is that they all had an h in common. So I'm going to factor out that h, and gives me 2x, looking for my other highlight, plus an h, and then plus this guy, plus 4, because we pulled the h out front, all over h. Well, that's convenient, because now h divided by h goes to 1, and I get the limit as h goes to 0 of 2x plus h plus 4. Can we evaluate that now? Yes. Substitute. Substitute in. What are we substituting? H equals 0. So I get 2x plus 0 plus 4, which turns out to be 2x plus 4. This is the derivative of our original function that we started with. This is known as the general derivative. For any x, right? So if you tell me an x, I can tell you the slope at that particular point. So part 2 of this question said, find the slope of the tangent line to f of x at 2. We'll figure that out. So let's answer this question next, f prime of 2. So step 2, f prime of 2 equals what? Well, I take f prime of x, my equation, 2x plus 4, and I just substitute, don't I? It's just like function notation. Plug in 2, I get 2 times 2 plus 4. We get a slope of 8. That means in our picture up here, the slope right here on our green line had to be f prime of 2 turns out to be a slope of 8. Up 8 over 1 sounds believable. It gets fairly steep there. What was step 3? Find the point at which the tangent line is horizontal. Okay, we'll do that in a minute. Let's figure out what the y value is. That's what it's asking you. So up here, maybe I'll just calculate it up here. F of 2, this is just nothing more than plugging in and evaluating the function at 2. So I get 4 plus 8, 4 plus 8, 12, minus 1, 11. So this would be 2 comma 11 would be the ordered pair that my red dot represents, 2 comma 11. Now, part 3. You would think that's a hard question. Find the point at which the tangent line is horizontal. If you just view this picture, I think you could probably figure out where there's a horizontal tangent line. Wouldn't you call it at the vertex here of the parabola that we would have a horizontal tangent line? And kind of looks like it's going to be -2, but let's solve it. So let me grab this, make this a little smaller so I can work with the horizontal tangent line. Okay, so step 3, horizontal tangent line. What is one characteristic about a horizontal line? Oh, the slope is 0. We know that the slope would equal 0. And we're really proud of ourselves, right? So how do I use that information? Well, I take the derivative and find out where it was equal to 0. We knew our derivative equation is 2x plus 4. And let's set it equal to 0. So I'm going to solve this so I'd have 2x equals -4. Therefore, x equals -2. At x equals -2, we can expect a horizontal tangent line. Not surprising, that's kind of what we thought, wasn't it? Just based on our graphing. That's a lot of, what we're going to be doing in Chapter 2 is working with these derivatives, finding slopes at a point, which is sort of unusual, but we can do it because calculus allows for it. Finding the derivative of a function is called differentiating. Long word, a lot of syllables. Notations used for derivatives. Never before have we had so many different notations, right? F prime of x, I was using this one. It's quite similar to saying y prime. Dy dx is another. And this one, so this one's saying the derivative of y, where this one's saying the derivative of the function f of x. Much difference between there? No, not really. So I could say the derivative, I want to take the derivative of, like we did before, x squared, I can't quite remember what that function was, 3x plus 7. Maybe I want to take the derivative of that and come out with 2x minus 3 or something like that. So this notation embeds the function right there so that we can see we're taking the derivative of this function and then here is the derivative. The last one is not very common. It just represents the derivative with respect to x of the function y, or of the y equation, I guess. So different ones. Why is there different notations? Because there was two people, I think it's like this, I should look this up. Two people that were the founders of calculus, Isaac Newton and, can't remember his first name, Leibniz. They were inventing calculus at much the same time and didn't overlap with each other. They were not in communication with one another. And one, Newton, he was kind of the y prime guy, and Leibniz was more the fraction style guy. And we'll see their influences throughout our work as we do it. All right, I am going to pause here and I'll finish the video with part C and D in part 2. Have a good one.